Good afternoon, and thank you so much for the introduction. Um, this topic is groundwater use estimation and pumping in GAMS. You might have seen footprinting earlier, but I saw a lot of sessions on sustainability and other things, so I had to change it a little bit the last couple of days. And also, there's been some really good learning that I had at the conference, so you'll see some of the snippets from that in the presentation. The overall story of this presentation is will be based on some examples I'll give you. These are actual examples, but they're for illustrative purposes only. I'm not trying to pick out faults or anything or raise fingers. It just shows the power of data and how we can use it to improve pumping estimates. Now, the basis of this presentation or the takeaway I want you to take away from this presentation is that recharge and pumping are too big to calibrate, quote, without independently estimating them. And if they are to be used, or the model is to be used for local level purposes only. What are those local level purposes? We'll kind of go into that. And then we'll try to kind of understand how pumping is estimated. Again, it's a known, sort of an unknown. We know, oh, I guess I'm getting an echo here. So, wow. Let's try this. So it's kind of a known unknown. We know that we do not know certain amounts of pumping, so it's a known unknown. But the spatial allocation can sometimes really be unknown unknowns. So I'm going to try to keep it simple, try to keep it light. I'll have some jokes, but there's a couple of slides of math, so watch out. I gotta wait for myself, I guess. So we had a snippet earlier. Somebody was quoting Peter Drucker or Edward Deming, depending on who is attributed this quote to. You can't manage what you can't measure. Now, these folks are also attributed another quote, which is, measuring something doesn't make it more important. It's just more measurable, right? So if you're measuring pumping or you're measuring time, doesn't make time more important or pumping more important. It's just more measurable, and you have useful information for decision making. That just my text I added there, that what we're really looking for is useful information in that measuring part, right? How do we measure those? One is direct measurement. Talk about time, right? How can we measure or manage? How can I keep myself on schedule if I don't know what the time is, right? So I'm using that time to inform me. An example of how we can directly measure pumping is meters, right? That's the most direct measurement of pumping there can be. The other thing is indirect, but it's an estimate. It's sort of a surrogate, right? So if you want to estimate how kids are doing in school, or how good a certain candidate is, you look at their GPAs. It's a surrogate. Doesn't really tell us a lot about them, but it's one measure of it. So it's an estimation point. And so estimates get better when you have more independent points, right? That each one gives you more information. And that's one of the themes we'll have through our presentation. What are we doing all this for, right? Comes back to management. Groundwater management. We need these estimates and everything else that we're doing here for groundwater management. In Texas, it's mostly two things. On sort of a TDUB regional scale level, it's desired future condition process, right? But also, and we heard this in that really nice session today hosted by Natalie, groundwater availability studies for development, right? So I added that part after I went to that presentation and had a quick sort of a talk with John Dupnik also, because there's an analog there, right? People were saying, oh, you keep adding pumping, and nobody knows how much pumping has really gone on, so it's really hard to keep track of things. It's the same thing that happens in flood studies. You get all these permits taken out on downstream basins. Everybody starts developing, and upstream is still developing. Nobody's keeping track of anything. And sooner or later, you don't update your models or your stream flow estimates. It increases stream flow when there's a big precipitation event, massive floods. There's a direct analogy there with what happens with these groundwater availability studies. A lot of consultants do them. We're not really interacting with each other, not really being, the models are not being really updated, so we don't know how many other wells would be interfering. Now, when you have a drought condition, when these wells really start pumping at their permitted levels, they'll go dry, right? So they won't really perform. Now keep this in mind, sort of keep this in the back of your head. We'll come back to it later, right? So what we'll go to now is directly back to groundwater management and sort of the desired future condition process, right? This is what our models are generally used for. DFCs are generally set on these primary sort of criteria. Groundwater levels, so example, 48 feet for all of GMA 13 for the Carrizo-Wilcox, right? Percent saturated thickness. Again, I'll take the GMA 13 example. You'll know pretty soon how. 75% in the outcrop. And I think the years are 2080 for this round. And drawdown. So drawdown at a certain point in time. 30 additional feet drawdown in Trinity. That's examples from a GMA 9. And sometimes, just to mix things up, you know, those folks at GMA 8, right? Groundwater surface water interactions, such as stream or spring flow, right? So 100 acre-feet a month in Bell County for Edwards Balcones fault zone. So now it gets interesting because all the three above I can do with a regional scale analysis. I can do with my GAMs. That's what GAMs are built for, right? We talked about this a little bit, and Mike Keister hinted at it, that, you know, we're not looking at local level scale here. We're not looking groundwater availability studies, one well. Can't really use my GAM for that because that's not what they're built for. So same with groundwater surface water interactions, right? We can't go too local because that's not what GAMs were built for. So again, the snippet from, you know, these talks that we've been having this last couple of days, a lot of people are starting to talk about groundwater surface water interactions, stream spring flow. So local level analyses are really important. So two big themes here, right? Regional analysis, local level analyses. Groundwater availability studies, same thing. We're doing groundwater availability studies and giving it to the GCDs, and what we're telling them is, oh, the groundwater level we expect it to drop this much, or this much percent saturated thickness, or this much drawdown at a certain point in time, 10 years out, 20 years out, 30 years out. These also need local level analysis. GAMs are not built for this, right? But at the same time, if you just do a TICE type analysis and just do a pump test, it's telling you nothing about what's happening in the regional sort of sphere, right? And that's the dilemma that, you know, Mike pointed out to. How do you bridge that gap? So what is a regional level analysis? So I'm going to take this example from the recently updated GAM. I'm going to use this example continuously. I think it's very important. So again, regional level, and these GAMs are built for regional level analyses, right? So really good calibration. We're looking at all these parameters. They visually look good. Everything should be on that one-on-one line. It is kind of on the one-on-one line. Quantitatively, again, taken from the presentation there, slides available publicly. The statistics there at the right bottom, really good, right? Scaled RMSR for 3%, pretty awesome. So models really well calibrated for these regional scale analysis for DFCs and other things, right? We're gonna go kind of zoom in into some counties now, and we're gonna go Dimmitt Webb counties, right? This is something I noticed at the presentation and was kind of bothering me, so I did all this analysis on it. So this is just kind of taken from water data interactive at PWDB. I'm not sure how to use that. But somewhere in that red zone towards the south of Carrizo, Wilcox, you'll see DeMitt and Webb counties. Lots of wells out there, right? So when we start looking at what's happening at the hydrographs at the local level, we see a good trend match, right? It's really good. But if you're doing a groundwater availability study, you'll see, oh, we're off by 50, 60 feet. Is that good enough for me? I don't know, right? So we're kind of thinking through that. We look at some other wells. Okay, now we're having an issue because my targets now, right? So the observed are those dots. And if you go really sort of close in time to like recent times, 2012, 2016 kind of, so sort of extreme x-axis increasing, you'll see observations really dropping, but the simulated model is not dropping. Now, it's still matching the trend, which is what the model is built for, right? But if you want to use it for groundwater availability analysis, I mean, take a step back, right? Something similar, another one now. This time, the simulated is higher. Observed is lower, and there's a kind of a divergence, so the trend is really not matching. So we're really off now. But again, when you look at the statistics, you're going to get decent statistics because some is higher, some is lower, right? So what is going on with our current model development process that we can improve so that we have this sort of local analysis sorted out, right? So what we're doing right now is we construct a model. We have some initial estimates of recharge or pumping and hydrogeology. We put our grid together, we start calibrating, and we throw everything into our calibration, right? Everything, recharge, pumping, everything is a parameter. And great, I mean, we got so many new tools now and everything, but conceptually, let's take a step back and see if that's the right way to go about it, but can we spend more time maybe doing more independent analyses, more independent estimates of recharge and pumping, right? So let's take a step back now and take another ball in hand, which is just a little bit of math, right? So, and it's not even math. I'm going to try to go one-on-one. What is groundwater modeling, right? There are two steps to like the basics of groundwater modeling. One is the physics of groundwater flow, which is really easy. Water flows from a higher head to a lower head, right? Nothing really like rocket science there. If you have a slope, you roll a ball rolls downhill in surface water analogy, right? The other one is that your water budget checks out, right? So you have water in, you have water out, right? So water in, water out, and the change in storage is how much my head changed. But if you combine both of these, right, then, and don't get scared, you get the Moffler equation, which is what the GAM program uses for their models, right? Stay with me, I'm not gonna do anything with this equation other than just explain what's going on so we can better understand where recharge and pumping come in here, right? So your change in groundwater flow in space and any source or sink equals the change in storage, right? Kind of. So here's a very simplistic way of understanding it, right? So your Q is really your recharge, your pumping, your discharge, everything. So why is that Q important? Because it seems like everything else is going on and you just have that Q sort of sitting by itself. Is it really that important? It is important. And again, going back to the recently updated GAM, but this could have been taken from any GAM and pretty much any regional model here. And that is that the largest inflow to the model is recharge. The largest outflow from the models is generally groundwater pumping. So your biggest water in minus water out, your entire water budget depends on these two big things, right? So a little bit of math. Again, your change in head, how much my drawdown will change over time, right? It depends a function of your parameters, hydraulic conductivity, storativity, and the Q part, recharge and pumping, right? Now, the interesting part is K and S sort of behave very similarly, right? You have high permeability, you have a low drawdown, right? Your aquifer is really conductive. So your water level won't change much because the aquifer is moving it really quickly. So everybody kind of behaves a similar way. But recharge and pumping sort of pull at each other. The more recharge you have, the less your head will drop because water is just coming in. It won't let it drop. But the more you pump out of it, water is going to drop more. So very intuitive, right? So what are we doing? Again, when we go back to the model calibration part, where we're really like making the model ready for what's going on in the world, we're throwing everything into our calibration, right? And on a regional sense, we do a decent job, but when we come locally, we become really off because mostly recharge and pumping, we've not really put enough effort into looking at them locally, right? So KNS, highly heterogeneous, but directly we can measure them by some sparse pump tests which are available. They're expensive, so there's a calibrated parameter. It's a usually accepted practice. But for recharge and pumping, we can reduce bounds on these, right? Now they're hard to estimate recharge, and it's a separate topic, but we've done some studies before. You can estimate it on some simulation models, remote sensing methods. But for pumping, which is what we're discussing right now, it's almost everywhere, right? It's distributed. Some is metered or surveyed or reported, but a lot of it is just estimated. And how would we estimate pumping? So the purpose of pumping estimates in GAMS is groundwater management. That's what we're using it for in GAMS. But why are we really pumping it? So what is the purpose of pumping in the real world? Is because we add some attributes to it. We're pumping because we need it for something. Irrigation, municipal, power, manufacturing. A lot of these are reported. A lot of these we're metered, right? But some, we really have no clue. And those are the example I'll pick. So one of them is mining. It's Railroad Commission. ONG is pretty much exempt. They can do whatever they want, right? So really hard to know what's going on, right? Livestock domestic, again, exempt for the most part. But again, hard to find out what's going on. Why we chose Dimmitt and Webb is because it's frack country, right? So much oil and gas manufacturing, so many enhanced oil recovery wells, so much mining going on. So let's look at those water levels again, right? You remember those water levels going down? Now let's look at what was the actual pumping that was put in the model for Dimmitt, right? So now stay with me. First column, this is what they conceptualized. This is before they started calibrating. Second column, this is what they simulated. Third column, this is the water use estimate from TWDB. Fourth column, this is the USGS fresh groundwater usage. And then you have mining usage on the other part. And what you'll see is they're really underestimating and putting pumping in, right? Now, is that a big deal on a regional scale? Maybe not, because irrigation, everybody else is pumping hundreds and thousands. This is a few thousand somewhere, right? But in some local cases, this can be really important. And why we've isolated this case is because in other counties, it's really hard to take the impact of one use versus other. This is just such a simple, clean case, right? Similar thing happening in Webb. So in this case, you're kind of almost underestimating by a factor of 2, like half. If you go to Webb County, you're off by almost a factor of 10, right? So the simulated pumping is in the 500s, while BEG estimates, which are exactly the same as what the TWDB now estimates, is like 3,000 or 4,000, right? So if I start increasing my pumping, I'm going to pull that bar down. My simulation is going to start matching, right, my observations. But in some cases, that might not happen, right? If I start pulling my pumping down, that red is going to go down, and there'll be more difference. So what's more important? What's another step to this? Is not just county level estimates, but actually figuring out where that mining use is happening, right? So this was sort of recently developed for a study done by LRE, and I was part of a part of it for the mining use, and it's available on the web. They have a website there. So it's really hard to figure out this mining use because it's underreported, A. B, what we came up with our methodology was, first, look at databases, see what wells are tagged. Then also look at Railroad Commission data sets, see where the EOR wells are. So we have pumping wells, we have EOR wells. Then we correct for overlaps. And we, at the end, if nothing works, we figure out a diffuse pumping. But even in this scenario, at least you're going according to what the maximum or the appropriate pumping is. Here are some other ways to estimate other stuff, other uses. I think I'm running out of time now, maybe 2 or 3 more minutes left. But municipal, again, you can look at that report. There are direct methods, reporting, surveying, but there are some indirect methods that people can use and have used in other parts. Irrigation, something very similar, direct through reporting, and also through water budget analysis. There was a good snippet yesterday on OpenET usage, and I was just talking to someone about it. OpenET is starting to be used for irrigation estimates. I looked into it, and downloaded some data, and also went through the website. There are some really big mass balance issues with OpenET data, so just kind of keep that in mind if you're using that or taking that strategy forward. I'm almost off by like 10%, 15% on daily and sort of annual basis. So that correlation, you got to keep that in mind. So coming back to that analogy, right? That what's happening in the flood world, what's happening in the water world. Why don't we just update these models? Why just do it every year, right? That'll fix everything. It's because it's really expensive to construct these regional scale models frequently, right? So what do? So can we use GAMS for local level permitting? No, that's not their purpose, right? But we can extract that information, and now there are tools available where we can automate that process. So there will be some moderate effort because it's going to be county specific. Hydrogeology is so local. So that first effort has to be there to find that correlation between other parameters and recharge and pumping, because again, this is surrogate estimation, right? An independent estimation from different sources. But once you've done that, it's really easy to keep or maintain that update going forward. So that's one way. The other way is using local analytic element methods, sort of a mirror image approach, right? And again, these are also transferable. The initial effort would be moderate effort, but that's another thing that GCDs can do is build these sort of analytic models and use them for their permitting process and automate the other parts of it that can be updated as in real time. You get more precip data, you get more ET data, recharge gets updated. You get a new permit application, you can update your pumping. Groundwater database, submitted driller's report gets updated, it gets pulled into as a pumping well, right? So that was my presentation, some references.